Hello, very good evening. So we are going to continue with the fifth video about thermochemistry, where we are going to continue on with Hess Law. All right. So what is actually the main principle of Hess Law? Hess Law stated that when the reactors are converted to form product, enthalpy change of a reaction is the same. Okay, whether the reaction take one single step or a series of steps. All right. So what does it try to say in here? Now, let's say we have a path 1. So the path 1 straight away convert from reactant to products in here. So let's say this is an exothermic that takes only one step. Okay. However, there is an alternative path where in the path 2, you have from, let's say, A to become B, B to become C, or C to become D. So it is to say that no matter you are taking the one step or the series of steps, enthalpy change of the reaction is going to be the same. The delta H, the overall delta H is going to be the same in here. Okay, so in short, we say that total enthalpy change is equals to H2 plus H3 plus H4. Okay, so that is what Hess Law trying to say here. Okay, so there are two postulates that can be applied whenever we are applying Hess law in here. So what are the two postulates? Number one, the magnitude of the equation is proportional to the number of mole. So let's say when you burn 1 mole of methane, you release negative 890 kilojoule per mole. Now you burn 4 mole of the methane. So the total enthalpy change of the reaction in here will be multiplied by 4. So you have 4CH4 plus 8O2 give 4CO2 plus 8H2O. Total enthalpy change of the reaction is the negative 3,560 kilojoule per mole. That means basically you just multiply by 4, right? The second postulate that we can carry out for when applying Hess law is that all thermochemical equations are reversibles. So the magnitude remains the same, but the vector changes. So let's say in the lattice energy, Na plus gas plus Cl minus gas give MaCl. So this energy is negative 770 kilojoule per mole. So when you reverse it, when you have NaCl give Na plus gas plus Cl minus gas, magnitude is still the same, positive 770, but the vector changes from negative to become positive. So this is how we can apply the Hess law here. So maybe if we just describe like this, you won't be probably not able to understand fully. So I will make use of examples in order to make sure that you understand better on how to apply Hess law in here. All right. Okay, so from what we have learned so far, so Hess law is not about the path dependence, it's path independence. The vertical drop of the delta H is identical whether transverse in a single step or multiple step, and the vectors of the magnitude scales directly with the moles. Reversing chemical equations physically flips the vector by perfectly inverting the delta H sign, and the left-hand side and right-hand side annihilations, where intermediate substance at the opposite side are usually subtracted, whereas the species at the same site usually are added together in here, right? So this is very important when we are about to apply Hess law. So let's begin with some of the basic examples that I've specially prepared for you. Okay, you ready? Okay, so let's say if now you have, eventually we want to identify what is the enthalpy change of the formations for carbon dioxide. So we are to determine the enthalpy change of the formation of carbon dioxide. Okay, so you are given two equations in here where C plus half O2 gives CO. So this C plus half O2 gives CO. The enthalpy change of the reaction is, let's say, negative. How many? I think I forgot already. 283 kilojoule per mole. Okay, and the oxidations of the carbon monoxides, okay, combustion of the carbon monoxide, okay, is equals to negative 110 kilojoule per mole. Okay, so now we want to determine enthalpy change of formation for carbon dioxide using equation 1 and equation 2 in here, right? So as a result in here, you will be able to see that. So you have the CO cancel with the CO because they are made from the same species in here. So the enthalpy change of the formation, which can be written as carbon solid. Okay, you can see from here. So this is the overall equation made out of 2. So you can see from here, carbon solid, okay, plus half O2 and half O2. Now, because they are at the same site, we cannot cancel them. So instead of cancel them, we sum them together. So plus 1 O2 gas give CO2 in here. So the enthalpy change of the formation for the carbon dioxide is summation of the enthalpy change, therefore negative 393 kilojoule per mole. Okay, all right. So other than solving using Hess law, this process can be explained in the form of energy level diagram. Energy level diagram. Okay, so how are we going to express the energy level diagram for this one? So for energy level diagram, right? So you have the y-axis, which is usually labeled with energy in kilojoule, right? So you have the changes from state A to become state B to become state C in here. So each of them are representing by their respective chemical changes or physical changes. So even from solid to become liquid, certain changes, so they absorb heat, correct or not? So that is why the energy level diagram is used to represent them, okay? So in the case of just now, the carbon dioxide case, okay? So where you see just now, the overall reaction is where, okay, so this is the energy level diagram. Okay, don't forget to put the y-axis in here. Okay, so y-axis, you put energy, kilojoule. Okay, so just now, this one step is from carbon plus oxygen give carbon dioxide. So we say that it's negative 393, correct or not? So this is the one step in here. Okay, and then you have just now in the equation 1, we have C plus half O2 gives CO. This will release negative 110. So since this process is exothermic, so exothermic means that reactant high, product low. Okay, so this is exo lah, negative 110. So you see from carbon plus 1 oxygen form carbon monoxide. Carbon monoxide only uses half oxygen. You notice that? So in here, you only uses half oxygen. What will happen? So you have another half, which is the unused oxygen. So the unused oxygen out of this one, it now becomes half O2. And this will help us to complete the remaining cycle where our second equation is CO plus half O2 gives CO2. So do you see that? CO gas plus half O2, this will release a total of negative 283 kilojoule per mole. So you form CO2 in here. So do you see how the interpretations goes by where the Hess law stated that enthalpy change of the reaction is the same no matter the reaction take one steps or series of steps here. Okay. So that is how you are going to express in the form of Hess law and also in the form of energy level diagram. So we are going to see more examples. So the next example is the oxidation of O2. Now, let's say if we have 2 SO2 plus O2 give 2 SO3. Given to you, enthalpy change of reaction is what you want to find. So you were given the following information. You were given the formation of the carbon sulfur dioxide. So the formation for the sulfur dioxide can be written as S sulfur plus O2 gas give SO2, enthalpy change of formation is negative 297.0 kilojoule per mole. And then you are also given enthalpy change of formation for the sulfur trioxide. So you will have to write the equation S plus 3 over 2 O2 give SO3. So this will release a negative 396.0. So now what we want SO2 and O2 to be at the left-hand side of the equation. We want SO3 to be 2 SO3 to be at the right-hand side. If you look at equation 1 and equation 2, you can see that now SO2 is at the right-hand side. Do we want it to be at the right-hand side? No, we don't want. So we want it to become left-hand side. What do? We reverse it. And not only that we want 1 SO2, but now we want 2 SO2. That means the whole equation in here, not only that you reverse, you also multiply by 2. So as a result, what do you get? So you get the equations as 2 SO2 give 2S plus 2 O2, and enthalpy change become positive 594 kilojoule.
Whereas in the second equation in here, so now you have 1s plus 3 over 2O2 give SO3, delta HF is negative 396. But in here, okay, SO3 is already at the right-hand side, right? But how many SO3 we want? We want 2 SO3. So in other words, the equation in number 2 in here, everything multiply by 2 in here. So when you multiply by 2, so you have 2s plus 3O2 give 2SO3 in here. Do you see that? All right. So now, after deriving from the Hess Law principle, so we are ready to cancel or add on based on this one. So you can see that 2 sulfur cancel with 2 sulfur, 3O2 cancel with 2O2. How many O2 left? 1 O2. So as a result, you shall have 2SO2 gas plus how many unreacted oxygen? 1 O2 gas give 2 SO3 gas. So the summation is positive 594 plus negative 792. So you have delta H of the reaction is equals to negative 198.0 kilojoule in here. Okay, so this is how you are going to apply Hess law inside here. All right, we are going to continue on how to express all of this inside an energy level diagram. So for energy level diagram, what do we do? Now we have three equations. So what are the three equations? So whenever you are trying to express energy level diagram, we try to keep the originality of the equation. What do I mean by this? Just now, you were given enthalpy change of formation for SO2, enthalpy change of formation for SO3, and you also were given to find the enthalpy change of the reaction in between two SO2 gas plus O2 gas give 2 SO3 gas. So this will release a negative 198 kilojoule in here. Okay, so now based on the equation, because you want this balance based on the law of conservation of mass. Okay, so even in your enthalpy change of formation, even though we write 1s solid plus O2 gas give SO2 gas. Now, do you ever think that this will be balanced between the SO2 and S in here? No, because the fact is that we need two SO2. So in here, we still keep the originality where this process is an exothermic process, negative 297 kilojoule per mole. So we have to multiply by 2. So when you multiply by 2, you get 2SO2 plus 2O2 give 2SO3. So instead of 297 kilojoule per mole, it now becomes negative 594 kilojoule. Okay. Now, as for the SO3, because we want 2 SO3, isn't it? So similar to the case of SO2 in here, we also multiply the enthalpy change of formation, everything by 2. So you have 2 SO2 plus 3 O2 gas give 2 SO3 here. Okay, so this will release delta H is equals to negative 792.0 kilojoule. Okay, so now whenever you are trying to build up the energy level diagram, we always look at this energy level diagram has two sides. I always like to put it in this way. It has two sides. I would like to call this as a left-hand side, okay? And I'll call this as a right-hand side. So Hess Law stated that both side total energy level must be the same, despite of the positive negativity. Okay, this one just coincidentally everything is exothermic, so everything is negative, but there are certain cases that some of them are endo, some of them are exo, but we don't mind about that. What we mind is the total energy at the left side will be equal to the total energy at the right side. So now you sum up 594 plus 198 is 792. Okay, don't look at positive negative. In here you also have 792. So from here you should know that SO3, the formation of SO3 stand on its own. It is the one step lah. Okay. Whereas the remaining 2SO2 plus O2 give 2S plus 2O2 give 2SO2, and also 2SO2 plus O2 give 2SO3 are the more than one steps here. Okay. All right. So how are you going to construct here? So I'm going to erase all of this. Okay, so we start off first from always the largest. So the largest is where you have 2S plus 3O2 give 2SO3. So it releases negative 792. So since this is exothermic, always make sure that when exothermic, reactant high, product low. Okay, then you draw the arrow goes down, showing that it is an exothermic. Okay, so we finished one side already. So let's go to the other side, which is here. So on the other side, okay, we still start from the above here. So the above, you have 2S plus 3O2. So now, based on the equation, we have the first equation where you have 2S plus 2O2 give 2SO2. So you see, you have 2S plus 2O2 give 2SO2. So the total enthalpy change in here is negative 594.0 kilojoule. Okay. So now from this step to this step is the formation for the SO2 times 2. Okay. Why times 2? You need to balance all the atoms inside there. All right. Do you notice that out of this reaction, this O2 is only part of it is reacted. You have only 2 O2 gas reacted. So how many oxygen unreacted? So you have 1 O2 unreacted. So this unreacted O2, you move it down together with it. Okay, so this is for the formation of the SO2, and from SO2 to become SO3. That's why you see just now the reaction, or actually combustion reaction of SO2 plus O2 give 2 SO3. Yes, this will release a total of negative 198.0 kilojoule. So in here you can see that the Hess Law principle will remain balanced if you do it correctly in here. Okay. So this is how we are going to solve Hess Law for this another example. Right, so I'm going to go for more examples to make you understand better. So far, all of our examples are showing exothermic, isn't it? Let's have a look from the perspective of the endothermic. So in endothermic, now you want to find the enthalpy change of the oxidation for NO. So you shall have 2NO plus O2 give to NO2. You are given the formation of nitrogen monoxide, where half N2 plus half O2 give NO. Delta HF is positive 46.0. Then you have half N2 plus O2 give NO2. Delta HF is positive 33.0. Okay, all right. So how are you going to manipulate in between equation 1 and equation 2 in order to get the overall in here? Okay, so as you expected, because at the overall, we want NO plus O2 to be at the left-hand side. We want 2SO2 to be at the right-hand side. There are two. So what you do is, to the first equation, now NO2 is already at the right-hand side of the equation. So what you need to do, so make sure that you reverse it. And then how many NO we want? We want 2, so the whole equation multiplied by 2. Okay? So at the end, you get what? So you get N2N, so 2NO gas give N2 gas plus O2 gas. So delta HF, delta H is equals to negative 92.0 kilojoule. Okay. Okay, now what about the second equation in here? So in the second equation, as you can see, you should multiply by 2 also, because you want 2 NO2. Do you see that? So everything inside the equation 2 times 2. Do you need to reverse? No need, because NO2 is already at the right-hand side of the equations in here. So you just simply multiply. You have N2 plus O2 give 2NO in here. Okay. So you are ready to cancel in between things already. Okay. So what are the things that you can cancel? So you can cancel nitrogen with nitrogen. So you can cancel. This one is 2 oxygen. So 2 oxygen cancel with 1 oxygen. So here no more oxygen. And therefore your overall equation 2NO. Okay. Plus O2 gas. Where is my O2? Okay, so 2NO plus O2 gas give 2NO2 here. The 2 is here. Okay, cancel like that. Okay. So your enthalpy change of formation in here is negative 26.0. Okay. So that is how you are going to balance the equation using Hess law. And I would usually advise students to write out what have you manipulated, especially in essay. Yeah, okay. Okay, so this is the how are we going to apply Hess law. Now, what about Born-Haber cycle? So a Born-Haber cycle, blah. What about Hess cycle? So in Hess cycle in here, as you can see, so now you have three equations. What are the three equations? Number one, you have 2NO gas plus O2 gas give 2NO2 gas. So as we calculated just now, this one is negative 26.0 kilojoule. And then you have N2 plus O2 give 2NO. So delta H is equals to positive 92.0. And then you have N2 plus 2O2 give 2NO2. So now you multiply by 2 but not reversing. So you are going to become positive 66 kilojoule. Okay. Okay. So as we mentioned just now, enthalpy change of reaction, no matter how many steps you take, is the same. So you take one step or a series of steps. So in here, when we compare in between the left and right, we are going to talk about balance. So in the left-hand side, total energy is 92.4. In the right-hand side, now don't look at positive, negative guys. Just separate these about. So 26 plus 66. So you have 92 also. So in another word, equation 1 and equation 2 are in one side. Equation 3 on this other side. On its own side lah, in here. Okay. So are you ready? Okay. So now you shall have N2 plus O2 give 2NO. N2 plus O2 give 2NO. Okay. So since this is an endothermic process, in endothermic, reactant low, product high. So arrow shoot up in here. Okay. So now throughout the boxes reaction, N2 plus 2O2 give 2NO. Does you use up all the NO? No, you didn't. So when you do not use up all the NO, so how many O2 actually you reacted? Only one. So this will become the unreacted NO. Sorry, unreacted O2. So the unreacted O2 will react with the 2SO2 to form 2NO2. So you have the enthalpy change is negative 26 as we calculated just now. Okay. And then finally, you have, don't forget, you also have N2 plus 2O2 give 2NO2 as we mentioned just now. So the whole thing in here multiply by 2, that's why you get 66. So once you do that, you will find out that energetically, this is 92.0, isn't it? The left-hand side lah. The right-hand side in here is negative 26.0 plus, don't look at negative lah, sorry for that, just now I did stress, 66.0, so total will also be 92.0. So do you see that it is balanced in both sides? So this is how Hess law is applied in some basic reactions, okay? So with that, I finished my 5th video. We are going to continue on with the 6th video later on. Thank you.